together with Mika, who is a master student, and Felder. So I will want to present our work we work with serverless workflows together with our using our AFCL abstract function choreography language. We build several workflows that we share with community. Those are montage, genome, PWA for bioinformatics and Monte Carlo. Workflows are different diversity, so if you need to use scheduling or any other research, you can use them. What is the good? Why this work is important? As Alex mentioned, focus on this. So the workflows are designed to be deployed on any region of Amazon and Google. For example, function in London can access storage to London or will run in Google London. And to all of this inside the workflow in the YAML, you can simply just change here one field, which is the resource, whether the function is on Google London or Google Tokyo or Amazon Tokyo, and then the workflow goes with data ins and data out of these functions. What some characteristics of these workflows? For example, here we can see that some functions download so many small files, and it can take even 20 seconds to download all those files, especially the merge function. So what we did in the meantime is we
you want to find what is the organization of times of people
from the storage. So we reduced the speed, the maximum in 20 seconds, so 1/3 of that. And another characteristic, let's say, for montage is that most of the functions are data intensive, so runtime or round trip time of the function is almost the same as download time. So compute time is less. But let's say for PWA, we see that most of the time is of the round trip time is the compute time because the upload and download time is very small. Regarding the providers, what we determined was that the download data and for download time and computation time of the workflows are mainly faster on Amazon rather than on Google. However, the functions that run on Google upload the data faster to the co-located Google storage. And then the next work, what we do at the moment now, is let's use these different data transfers between providers. So if I run the function in London, in Google London, can I use direct data from Amazon storage? And we determined that going from Lambda, AWS Lambda to Google storage is much faster rather than Lambda into its own storage. And so in order to use this, we develop the workflows in such a way that you can dynamically select which workflow we would like to use or which storage we would like to use. So we just change the URL of the buckets, and then we simply can determine which bucket to use regardless of so we don't need to code this inside the workflow. And in fact, what we achieve is we develop the functions with some kind of gray storages, gray function, and gray output storage, and then we can color simply by using the resource field. We can color the functions where they can run, and using the bucket or data ins and data outs, we can color the input buckets and the output buckets. And the workflows are publicly available here. Okay. So with this,
are there any questions?
Super fast. My first question is, how can it be possible that an Amazon Lambda can access more slowly data from Amazon storage than from Google storage and from the AWS?
Yes, I can understand. I can explain. For larger files, the bandwidth between Google storage is much larger. So we measured that for files above 3.5 megabytes, it's faster to store on Google London instead of Amazon London from AWS Lambda. For larger than 3.5 megabytes files, it's faster to upload to Google. Unfortunately, the paper was accepted. But hopefully, next time devices. Yeah. You can try. I can send you measurements. Okay, thank you.
Hello everyone, my name is Arjona. Solving Dynamics. So let's begin talking about the generic compute and data physics task. We're looking at the computational growth in data size and complexity from many genomic archives. And as a result, biomedical institutions struggle to pick up these complexity of data. So what we can do is leverage the cloud elasticity for scaling genomics models using certain resources. The problem is that this is complex for bioinformatics users. One main concern, for instance, is how many which is the capacity for processing a certain amount of data. So in summary, configuring, deploying, and scaling genomics models is challenging for bioinformatics users. As an alternative, what we can do is use serverless for genomic departments because the main attractive trait is that there is no servers to manage, and there is less friction to deploy for less experienced users, in this case, bioinformatics. Because FaaS allows us to pay only for the resources it provides instant scalability and is completely managed, and it allows to massively and effortlessly indicate genomic workflows. So our objective was to adapt an existing single node HPC variant calling Genomics application to serverless in order to scale in parallelism, process larger datasets, and decrease the overall runtime. So very fast variant calling, it's a genomics workload which detects differences in the genome. And we can do is use it for personalized medicine, preventive disease detection, etc. So here is our architecture. We adopted a MapReduce model. First, we do pre-processing to distribute the workload, partitioning the datasets. Then in the mapping phase, we compare all the sample genome, and this is a Cartesian product between the two datasets, which produces lots of parallel tasks. And then, since we distributed the workload, we need to reduce the partial results and generate a final result. So the main challenges here is how to partition the dataset, which is the optimal parallelism, and how we do this three-step map process. And I will focus on the first three of them. So first, with data partitioning, what we can do is leverage partial reads with byte range requests from object storage. So each lambda, here we have a large file, and each lambda will do a partial read from object storage. The problem is that doing arbitrary byte ranges will break the file format. So what we do is generate first an index file, so we can generate metadata for each partition. So we solve this problem about breaking the file format using arbitrary byte ranges. The second challenge we encountered is synchronous code and blocking the data dependencies, because this broke function calling functions pattern. So we had to stop the process, call another task, synchronize, and then resume. The problem with that is that there is no preemption in serverless, so blocked tasks will occupy concurrency slots and will limit the overall scalability. So that's bad for us. So as a result, what we had to do is split the blocking code.
So we have everything asynchronous, and each task can be scheduled independently. The problem with that is that the data dependencies have to be passed through object storage, which unfortunately is slow. And another challenge we had is how many tasks to launch, because we have fine-grained scalability with FaaS. The problem is that with more tasks, we have more parallelism, but it's less scalable because of the concurrency limit again. On the other hand, with less tasks, we have larger data chunks, and it's less efficient because accessing object storage is slow. So what we have to do is test a lot of configurations and measure processing time and storage input-output, as well as price. And then from all those configurations, we chose the most cost-efficient. And also we can leverage interfunction paralleling in order to launch less tasks, but without sacrificing the performance. So finally, we can evaluate this architecture. First, we compare with HPC, and we can see a considerable reduction in runtime because distributing single-threaded code significantly reduces the runtime. And then we proceeded to run some large-scale execution, which uses a realistic data set about human genomics, and it contains 1,200 tasks. And as you can see, the pipeline has different stages, which are very different in parallelism. And with FaaS, we can adapt the tasks throughout the pipeline execution. And also you can see that the default 1,000 concurrency limit is not a problem because we can schedule the tasks independently. So finally, as insights and conclusions, we can say that we successfully scaled a single node HPC genomics application using serverless, but we encountered many unique challenges that we had to undertake. And there were huge engineering efforts to adopt the serverless architecture because of that. And in particular, we outlined these 4 challenges. First, optimizing performance cost, balancing intra and interfunction parallelism. The second is data partitioning of unstructured data. Then asynchronous and non-blocking code to avoid concurrency limits. And finally, object storage, although it's the state of practice and it's scalable, it's still slow and it provokes elevated costs. Finally, this work is open source and can be found in this GitHub repository. And that was all. Thank you for your attention.
Thank you. Any questions? Okay, you can still ask the question even after the talk is finished. Trever?
Okay. One should already be open, but we can just open this again.
That one, yes.
Yes. And I talk into this one and this one.
Both.
Yeah, this one is
Yeah,
already.
this one.
Okay. Okay.
Turn it right.
Fine. Okay. Yeah. Hello. Welcome. I'm Trever. I'm from the Technical University Berlin. And my talk is called ProFaaStinate, Delaying Serverless Function Calls to Optimize Platform Performance. So we're in the world of, serverless computing. I think you all know what serverless computing is. So basically, users upload just the code they have. The platform does some magic based on that, and we get an application that is infinitely scalable, that has lots of hidden abstractions, which I actually like. But unfortunately, we have a little bit of unreliable performance. So in previous work, we have shown that the performance of Google Cloud Functions can vary by up to 14% between day and night. And some people also might say that FaaS is quite expensive. So yeah, what we are doing in this paper is we are increasing the amount of hidden abstractions we have to deal with the performance and cost problems. Our basic idea is that, well,
if you break it down a lot, the architecture of a FaaS system generally is, well, we have users, they send calls to basically an API, HTTP, for example, and this API just forwards all invocations to a component that is responsible for finding a function worker that will actually execute the function. And for synchronous calls, of course, it's very important for the users that this call is executed immediately because, well, they're waiting for the answer. But asynchronous calls are also executed immediately on FaaS platforms right now, although we are not really waiting for the response. So the general idea of our paper is, well, what if we just put all the asynchronous calls that are coming in and we allow developers to specify a deadline by which it's possible to just delay the execution of those asynchronous incoming calls. So what we do, every asynchronous call that comes in that is delayable, and we put that into a queue that is ordered by the earliest deadline first. And then we have a call scheduler that just only executes calls whose deadline is approaching. And to influence how the call scheduler works, we have two different states, busy or idle, and those states are influenced by, for example, the external load or whatever. So this state is a feedback control system. And whether we are in busy or an idle state depends on the platform-specific resource bottlenecks. Whether the platform has resources right now or not kind of depends on what workloads are running on the platform and what else. Of course, you need to watch out if you have those two states for hunting oscillation, which happened quite often for us in like the early phases of our evaluation, that you put the system in busy mode. So you put the system under less load, which decreases the load so much that it's in idle mode again, and then you put it in and then you increase the load again and put it back into busy mode. So for our evaluation, we have chosen to use a CPU restrained workload and system. And we say that if the CPU utilization is less than 60% for 30 seconds, we switch to idle mode. And if it's higher than that, higher than 90%, sorry, for 30 seconds, we switch back to busy mode. So this state that the scheduler is in then influences how calls are executed. And in the busy state, we say, okay, we only want to execute those calls which would exceed their deadline if we didn't execute them right now. So for example, in our case, we just look at the next 10 seconds and execute all calls which would expire in the next 10 seconds. So this is busy, but if the platform actually has free resources, then we say, okay, we want, of course, also to execute all those calls that would expire soon, but we want to execute at least n calls per unit of time. And of course, again, you would need to tune that based on the normal resource consumption of the platform to make sure that your platform can actually handle at least n requests per second. We have implemented this on top of Nucleo, which is an open source serverless platform written in Go that's, I would say, moderately easy to work with. And we have also implemented an example use case, which is a document uploading and analysis workflow. So users upload a document synchronously to a pre-check function. And this pre-check function just does a very basic check whether users have actually uploaded a PDF. And then they synchronously respond back whether the document is okay. They then put that into an object storage, which triggers a virus scan, which triggers an OCR function, optical character recognition, and then we send out an email notification to users. And the OCR is very CPU intensive. And if we allow the delay of functions, then we say, okay, we have 7 minutes until the virus scan has to be triggered, 7 minutes until OCR has to be triggered, and again, 3 minutes until the email notification needs to be sent out. And for our evaluation, we have decided that we want to put the system under a constant load of 1 request per second over 30 minutes. And what we are actually doing is we are putting the whole system under an artificial CPU load that is 80% in the first 10 minutes and 15% from minute 20 to 30. And in between, it just scales down linearly over 10 minutes again. And if we don't delay the asynchronous function calls, but just execute them immediately, we can see that the CPU utilization is, well, basically 100% for the first 17.5 minutes of the experiment, because we are calling this OCR function, which is very CPU intensive. And well, that just, yeah, packs out the CPU. And if we use ProFaaStinate, then of course we don't have to execute all those OCR functions right now. So because of that, we have about a 10% headroom during the times of high load. And you can see this little dip around minute 14, which then goes up again. And this is, of course, when the first function that we called, when the 14 minutes are over and we have to actually execute the OCR functions. But as we can see, by then the high load, which we artificially generated, is already over. So we have the room to execute the OCR function as well. And around minute 20, ProFaaStinate switches to idle mode. So it has to catch up a lot of invocations that it didn't execute earlier. So the CPU load is a little bit higher than a baseline. And actually, well, users are not really interested in CPU utilization, but they're interested in the workflow duration because, well, serverless is built per the minute, or per millisecond. And we can see that the workflow takes about 20 seconds while the system is overloaded in the baseline. And it's, well, way shorter using ProFaaStinate. So yeah, there's an elephant in this room. And if we ask the elephant to step aside, we see XFaaS, hyperscale and low-cost serverless functions at Meta, which was published at the end of October. I'm very grateful for preprints right now because we put out a preprint before that. But let's look at what they did. It's a very good paper. I can highly recommend it. And they have a solution for high variance of load because they employ time shift computing to postpone the execution of certain functions. And when XFaaS reaches its capacity limit, delay-tolerant functions are deferred to off-peak hours for execution. And well, because it's Meta and not some like some small researcher, they have trillions of function calls per day running on their system on more than 100,000 servers spread across tens of data center regions. And what I think is very interesting here, which is kind of a different direction than what we envisioned, is they don't have the problem that the platform is overloaded and they are like helping the platform to not be overloaded by delaying some FaaS functions. Their FaaS functions would actually completely overload their platform, because you can see here the load of a spiky function, and like once every day, they get 5 to 17 million invocations all at once. And of course, they would have to massively over-provision their system if they wanted to execute those right now. So they're just spreading out all of those functions calls over a whole day. But yeah, so this talk was actually about ProFaaStinate and not XFaaS. Our general idea was that some serverless function calls, if they're asynchronous, maybe can be delayed. And this allows us to essentially shave off load peaks from the FaaS platform, which leads to reduced cost and faster performance for users. Our scheduler is very simple. It has 2 states. It's idle or busy. And in the future work, we should look at, well, having more complex scheduling algorithms, which in turn, of course, also means that we have a more complex queuing mechanism. So yeah, thank you for your attention. And I don't know whether we have time for questions.
Yeah, we have 1 minute or more. Very interesting talk. Any questions? Yes.
Yeah. So, serverless, I mean, has low invocation time because the scheduling is very simple. So if you complicate the scheduling, this might affect the synchronous response time, which has to be very tight.
Yeah.
Or are you planning to deal with that problem?
I mean, we are kind of thinking, I mean, we don't need to have optimal scheduling, right? We only need to be kind of optimal in our scheduling. So essentially, I would just use like multiple instances of our system next to each other and just load balance between them, right? If we want to scale up. And that's also kind of what Meta did in their paper. They have like load balancers that are a little bit smarter and try to balance functions calls for a specific type towards the same system, right? And then this system can just deal with it itself.
Any other questions? Okay, thank you.
Okay, thanks.
Next speaker will be remote, so I'm going to switch. So I think we can see your screen. Can you try to speak?
Hello. Can you hear me?
1 second. Okay. Can you try to speak? You might be on mute.
Hello, can you hear me?
Okay.
Sound check.
Cannot hear you. Are you?
Hello?
Can you hear us? Xinghan, I can see you.
Yeah, I can hear you. Yeah.
I cannot hear you.
Can you hear me now?
Second, I will just check out your settings.
You need to put in this one.
Okay, great. Thank you for that.
It's probably, yeah, probably not. No, you have.
I have that.
You have your audio jack there, so you probably need to unplug this part again here.
No problem. Okay, thank you for that. Okay, can you try again? Hopefully now it's going to work.
Hello. Can you hear me?
We still cannot hear you. Can you hear us?
Yes, I can hear you.
Yes, okay.
Can you hear me now?
Okay, can you?
Hello. Can you hear me now?
Okay, we can hear you. Okay, can you say again something?
Hello.
It's very good now.
Okay, thank you. So I'm going to start.
You have
Hi.
10 minutes for your talk. Thank you. Go ahead.
Yeah. Hi, my name is Xinghan Chen, and today I will be presenting our paper x86 versus ARM64, an investigation of factors influencing serverless performance. In this project, we investigate difference in CPU utilization metrics, performance variation, and the cost of executing serverless FaaS function on x86 versus ARM64 processors. Recently, ARM64 processors has been adopted by cloud providers in data centers to provide alternative to x86 processors. The main benefit of switching to ARM64 processors appears to be their improved power efficiency and lower cost. For example, AWS Lambda provides a 20% discount for executing serverless functions on ARM processors. Staying with x86 processors, however, provides advantages including avoiding software migration costs while offering greater potential for performance optimization with a widely supported software environment. x86 processors also provide platform-specific abilities such as AVX512 advanced vector extensions, which are single instruction multi-data instructions which can be critical for certain applications. In this paper, we address the challenge of understanding the performance implication for ARM64 for executing FaaS function and workloads. We investigated the serverless function performance using a diverse set of workloads consisting of 18 functions scaled across 40 distinct time steps. We categorize these functions as either CPU user bound, CPU kernel bound, memory bound, or I/O bound. To support our investigations, we utilize the serverless application analyze framework known as SAP to collect runtime and CPU time accounting metrics. SAP support profiling function as a service workload performance, resource utilization, and the infrastructure to enable accurate performance and cost characteristic. To address research question 1, we investigate how Linux time accounting metrics varied between x86 and ARM64 processors. For most of our functions, both architecture exhibited similar CPU utilization. For NIMPAC and graph PageRank, those two functions have noticeably higher CPU user time on ARM64 processors, while both of those functions had a higher CPU kernel time on x86 processors. On ARM64 processors, these functions had greater runtime than x86, suggesting that x86 specific kernel functions were used to help optimize the performance. For research question 2, we classified the function performance into 3 groups: ARM faster than x86, ARM slower than x86, and ARM performance similar to x86. We categorize our AT functions into 3 groups. If ARM performance was 20% or more faster than x86, we classified this function into ARM faster group. If ARM performance was 20% or more slower than x86, we classified this function into ARM slower group. Otherwise, we classified function performance into ARM similar group. The graph shows we have 6 functions in ARM faster group, 4 in ARM slower group, and 8 in ARM similar group. On average, for 80 functions scale across 40 time steps, a total of 720 unique evaluations, ARM processors increase the function runtime by 2.86%. To address research question 3, we calculate the coefficient of variation of function runtime for both x86 and ARM64 processors. For 20 out of 18 workloads, ARM64 processors have a lower coefficient of variation, suggests more stable performance on ARM64 when executing functions on x86 processors. From this graph, we can observe that x86 performance tends to have more variability than ARM. We also calculated the coefficient of variation across 40 time steps for over 18 functions to examine performance variation when scaling up the function time. In most cases, ARM64 processors had higher performance stability than x86 across a range of function time. For research question 4, to compare the cost, we computed the cost difference between x86 and ARM64 processors on AWS Lambda for our 80 workloads. This graph depicts the estimate cost on AWS Lambda for performing 10,000 functions calls across 40 scaling steps for a total of 400,000 calls per function. We can see for most workloads, ARM64 processors provide a cost saving on AWS Lambda. Presenting the cost difference as a percentage, we see that only 3 workloads had higher costs on ARM64. Interestingly, these workloads were all workloads with higher runtime that can benefit from x86 specific capability. For example, the vertical-based single instruction multi-data extensions and x86 library optimization. Our other 50 workloads shows a huge cost saving from 5% to over 60%. On average, for our 80 workloads, scale across 40 time steps, a total of 720 unique evaluations, ARM64 processors reduce function executing cost by 18.4%. we conduct large experiments using both ARMS and x86 processors on AWS Lambda function to evaluate the performance of 18 workloads over 40 distinct time steps. For research question 1, while most functions had similar CPU utilization profile across both architecture, some functions on ARM64 had higher CPU kernel mode utilization. This difference may help detect where x86 versus ARM64 performance difference are likely to occur. For research question 2, ARM64 can provide performance advantage for serverless workloads. Of the 18 serverless functions tested, ARM64 provides faster runtime than x86 for 7 out of 18 functions. 4 functions were more than 10% faster of ARM64 runtime improvement appears highly dependent on the nature of the workloads. In summary, for our 18 worker functions, we observed that ARM64 processors increase the function runtime on average by 2.86%. Functions run on x86 processors on AWS Lambda exhibited more than twice the runtime variation versus ARM64 marketing x86 processors. This rely for consistent performance. ARM64 processors offers cost saving on AWS Lambda at observed of 15 out of our 18 functions. Some of the cost saving are attributed to the 20% cost discount offered by the cloud provider for ARM64 processors. In summary, for our 18 functions, we observed that ARM64 processors reduce function executing cost on average by 18.4%. Thanks to listening our presentation. Any questions? Hello, you don't have your mic on.
I'm sorry, we have repeated third time.
No, can you hear me now? So
Yeah.
you had many functions. Were some of the functions accessing the storage, and did you detect the performance differences towards the storage?
So for the functions that taking storage, that
Because
is
if you use different memory to the functions, then storage access time changes. So I was wondering if also the platform regarding CPU affects the storage access. Do you have such experiments? That was the question.
Thank you.
Okay.
excuse me, could you repeat? So for the storage, we are testing on the same configuration of for all of our workloads. So it's 3 gigabits. For AWS Lambda, this will give us 2 full core access. And we
can also follow up on Discord afterwards.
Okay.
Thank you all our speakers. That concludes the session number 1. We have now coffee break, and I think until 3:30, and hope to see you back. Thank you.